are a number of other assumptions in the study, and don't have time to drag you through all of that today, but that is one of the studies that you can find on the UIG website that I mentioned a little bit earlier. But what we're looking at here in the graph, we've got two panels. The dark blue up at the top represents the 5-minute load, and this is for just about 9 months worth of data. And what you can pick out some weekly, and if you've got good eyes, maybe even a couple of daily cycles here. But the point is that this is electric load without any wind generation whatsoever. This is what the power system operator has to live with and operate to on a day-to-day basis without any wind. The bottom part of this graph shows the 5-minute changes in the electric load from one 5-minute period to the next. And if you take a look, you see what's more or less a red band. There are a few places where you'll see an excursion from the midpoint of the graph. And those excursions represent periods of time when the 5-minute change in load was fairly high. Now, there aren't very many of those, but you see one at about halfway through the time period. You see a couple of those about a quarter of the way through the time series on the left, and you see a couple on the right. So basically the takeaway message of this graph is that the power system operator has to deal with quite a lot of variability even if you don't have any wind in the system. Now, if we go on to the next slide, we'll see what the impact is of adding large amounts of wind to the system. Now, this is a very high penetration rate. 25% of the energy is coming from wind in this case. The right-hand graph is the one that we just saw a minute ago, and I left it up here for comparison. The right-hand graph is what the system has to do, what the system operator has to do with this large wind penetration. And the basic idea is that for every megawatt of wind that I'm getting generated at any given time period, that's 1 megawatt that I can back down from my conventional units. And so what I want to do, once the wind turbines have been built and developed and so forth, the marginal cost of a megawatt of wind energy is nearly zero. Now, that's distinct from the capital cost, which is clearly not zero. But once the wind is on the system, the most economical way of running the system is to take all the wind you possibly can take. If there's a reliability issue, then we may need to take some sort of mitigation measure. But wind is going to be cheaper than gas, cheaper than coal, cheaper than anything else that you've got in your system. So the right-hand graph is saying I start with my load, subtract out the wind generation for each 5-minute period, and what I'm left with is what the conventional generation fleet has to operate to. Now, if you look at the difference in these graphs, you see that they are very different. The blue panel on the right, you'll see there's a lot more white space, and what that white space indicates is that the conventional generation has to achieve a pretty low level of turn down, as we call it. One easy way to think of this is that there are a number of periods, typically at night, when the load is low, but the wind is blowing and creating a lot of energy. So to accommodate the wind, what you would need to be able to do is to back down the conventional generation to a much lower turn down level than you would if you take a look at the left-hand blue part of the graph. So that's one of the key messages that pops out of this graph. The other one that's a little harder to see is that there are some pretty healthy ramps going on here on the right-hand side. Now, you can see a part of that by looking at the red trace at the bottom. If you compare the red trace on the right, which includes wind, and the red trace on the left, which is load only, you'll see that the thickness of that red band on the right is thicker than the one on the left virtually all hours, or at least all that we can discern from the graph. You also will see some larger ramps occurring on the right-hand side, more larger ramps on the right-hand side than what we saw on the left-hand side. So the takeaway here is that, and again, this is an extremely high wind penetration. 25% of all electricity is coming from wind in this scenario. At this high penetration, the conventional generation needs to be able to achieve a fairly low turn down point. It's an open question as to whether the generation fleet can actually do that, but here we're really looking at the needs of the system and the impact that wind would have if you could take all the wind possible. So yes, wind definitely increases the on to the next slide.